Yes. Okay, so just a reminder, this material is not going to be on the test on Friday. So this is just material that will appear on the final, but not on the test on Friday. All right, so we're going to talk about section 4.4, which is solving exponential and logarithmic equations. And Sabine, you asked me last class, why do we need all those properties of logarithms? This is where we use them. Okay. All right, so if we want to solve exponential equations, so those are equations where the variable appears in the exponent. The key, when you want to solve them algebraically, is to take an appropriate log of both sides. And you can take any log you want of both sides. I always go with the ln because it's only 2 letters, and so it saves me a little bit of writing. But you can take any log you want. You could take the common log of both sides. We generally take the ln or the common log because we have those buttons on our calculator. So that will help us get the answer. So if I want to solve 2 to the x equals 72, I can take the ln of both sides. The ln of 2x equals the ln of 72. So this is like the most basic rule of algebra, right? You can do anything you want to an equation as long as you do the same thing to both sides. So I am taking the ln of both sides of this equation. And then last class, we learned this really useful property that we're going to use over and over today, that if you're taking the ln of something to a power, you can take that power and put it down in front, and it becomes multiplication. So this is going to become x times the ln of 2 equals the ln of 72. And the ln of 2 and the ln of 72, those are just numbers. You could put them in your calculator, you'd get a decimal. Those are just numbers. So to get x by itself here, I'm going to divide both sides by ln 2. Okay, so my ln 2's cancel on the left, and we get x equals ln 72 over ln 2. And that is what we would call the exact solution. That is an exact value. As soon as we put it in our calculator, it's going to round. Yeah. So if I want a decimal, I can type it into my calculator, but that would not be an exact value. Okay, so let's see. ln 72 divided by the ln of 2, and I get about 6.17. And then just to check our work, we could plug that number back in, right? So this is the beauty of when you're solving an equation, you can always tell if you're right, because if you plug that number back in for x, your equation should be true. So let's try. If I do 2, and I'm going to use this exact value, I'm not even going to round the numbers. I'm going to say to the previous answer, I should get 72. And I do, so I know I'm right. The second negative sign, ANS, yep. The other thing you can do that's really handy is store a number. So I'm going to pull up ln 72 over ln 2, get my decimal. If I know I'm going to use that number again in another calculation, I could store that number as, say, the letter A. So use this STO button, store, and it's saying, okay, take that answer and store it as, that's the little arrow. I want to store it as the letter A, so I press alpha A. Now that number is stored as the letter A. So now if I want to do 2 to the letter A, I should get 72. Just a handy little thing to know. Okay, you try B. See if you can solve e to the x equals 25. All right, so let's go through the whole process here. So e to the x equals 25. Basically, you generally take the ln of both sides. That is how we free a variable from an exponent, right? We say, oh, e to the x is stuck up in the tower, right? So how do we get the x out of the tower? You use a log, climb a tree, right? So So I use take a log of both sides, and that allows me to free that exponent from its tower. So we have x ln e equals ln of 25. But what is the ln of e? Think about the definition of a logarithm. What is the ln of e? It's 1, yeah. Because when I say the ln of e, I'm saying what power should I raise e to get e, which would be 1. And if you didn't know that, you could type ln of e, and you get 1. Right? But you should know that for a non-calculator test. You should be able to evaluate the ln of e. Yeah. All right, so ln of e is really just 1. So this says x times 1, which is x, equals the ln of 25. And I can get an approximate value for that using my calculator. And I'd get 3.21. 22. And again, this guy is exact, and this guy is approximate. What's that? It's like leaving a radical. Yep, exactly, yeah. So if your homework asks you to give an exact answer, you would leave the ln's in there. If it asks you to round or give an approximate answer, then you use your calculator and put in a decimal. All right, so let's try solving some slightly tougher ones. The key to each of these is going to be to first isolate your exponential expression, then take a log of both sides. So in part A here, my exponential expression 2 to the 1 minus x is already isolated all by itself on the left-hand side. So the variable is stuck up in the exponent, wants to come down, so I take a log of both sides. So I'm going to take the ln of 2 to the 1 minus x. That equals the ln of 3. So now I can use my great property of logarithms that lets me take my exponent and bring it down in front. So I'm going to take that whole exponent of 1 minus x and bring it down in front of the ln of 2. All right, now what do you want to do? Divide by ln 2. Is there anything else that you might want to do here? Yes, that's after you divide by the ln 2. But is there an alternate thing you could do instead of dividing by ln 2 here? You could distribute, yeah. ln 2 is just a number, right? So I could distribute and then solve, or I could divide by the ln of 2 right now, as long as you're pursuing the goal of getting the x by itself, right? So I can do either thing. I'm going to divide by ln 2. So over here they cancel. ln 2 is just a number. So I end up with 1 minus x equals ln 3 over ln 2. And then I'm just going to, ln 3 over ln 2 is just some number, right? I could type it in my calculator, I'd get a decimal. So I'm going to move the x to the right and the ln 3 over ln 2 to the left, and I get x equals 1 minus ln 3 over ln 2, which is approximately negative 0.58. And we should check our work, right? If you're solving an equation, you should always take your answer and plug it back in. So I'm going to store this number as A, store as A. And then I'm going to double check 2 to the 1 minus A. When I hit enter, what am I expecting to see? A 3. Good. All right, so for B, like I said, the goal is to isolate the exponential expression. What is the exponential expression in this equation? E to the 0.3t. So first step is to get this by itself. All right, so what do I do first? Subtract 100. Right, so I get negative 100 e to the 0.03 t equals negative 90. Divide by negative 100, so I get e to the negative 0.03 t equals 0.9. So now I've isolated my exponential. To rescue that variable from the exponent, I'm going to build a log. Take a log of both sides. Lincoln logs, I like it, yeah. So I'm going to take the ln of e to the negative 0.03 t. Oh, nope, I don't know why I wrote negative, sorry. Equals the ln of 0.9. All right, what is the ln of e to the 0.03 t? 0.03 t, yeah. The ln of e to some stuff is always that stuff, yeah. It's a plus, because I accidentally wrote a negative, so then I made it a plus. You got it. All right, so the ln of e to some stuff is always the stuff. And then to get the t by itself, divide by 0.03. So we're going to get t is the ln of 0.9 divided by 0.03. And that is approximately negative 3.5. I looked at this expression and I used what I know about logs to say the ln of e to the 0.03 t. That's asking me what power should I raise e to get e to the 0.03 t. It's just 0.03 t. You can also think about it as taking the exponent down in front, right? So it would be 0.03 t times ln e, but the ln of e is 1. So it ends up being 0.03 t. Yeah, the base of ln is e. If what was 3 ln? Like they just say instead of it being it was 3 ln to the e. Like that? Yeah, it would still be the same. This would be 3 times the ln of e to 0.03 t is 0.03 t. Yep. So in general, the ln of e to some stuff always gives you the stuff. Because ln and e to the x are inverse functions. So it's like one thing, ln undoes e to the, and e to the undoes ln. So if you take the ln of e to some stuff, it's like, remember when we first talked about inverse functions, right? So if this is e to the x and this is ln x, right? If I put some stuff in here, right, out's going to come e to the stuff. And then I drop that into the ln. These are inverse functions. They undo each other. So the stuff should come back. Yep. Yeah, when you can, we just get rid of logs. Yeah. Yep. Oh, it's not so bad. Maybe it is. I don't know. All right, so what do you think we do here? So the first goal is to isolate the exponential, but I have two exponential terms. And each one is isolated on one side of the equation. That's the best we can do. So the next step, subtract 1 and make it equal 0. It's not a bad idea. Let's see what happens. Okay, now what do you want to do? Are they like terms? Yeah, if it was 3 to the 2x minus 1 times, no. Yeah, because the order of operations says you have to do the exponents first before the subtraction. And because you don't know what x is, you can't actually do the exponents, so you can't simplify that. Out of idea. Okay, so we don't want to do this. Yeah, if I take the ln of both sides, I'm going to have the ln of 3 to the 2x minus 1 equals the ln of 7 to the x plus 1. And that will allow me to take both exponents out of, both variable expressions out of the exponent. Yeah, so I'm going to have 2x minus 1 times ln 3 equals x plus 1 times ln 7. And ln 3 and ln 7 are just numbers, so this is a simple equation to solve. It just is going to get ugly because ln 3 and ln 7 aren't integers. So I'm going to left to you. You can work on that later. Okay, so remember the rabbit population. We talked about this several classes ago. It started with 1,000 rabbits and doubled every year. How many years will it take for there to be 50,000 rabbits? Okay, so we came up with an equation for the number of rabbits. We had r of t was 1,000 times 2 to the t. Right, because we started with 1,000 rabbits and then you multiply by 2 over and over and over again. And repeatedly multiplying by 2 is like multiplying by 2 to the t. All right, so how long until there are 50,000 rabbits? So how many years means I'm going to be solving for t, and the rabbits is 50,000. Okay, I'm going to give you a few minutes to try this one before we go over it. Okay, let's go over it. So when you're solving an exponential, your first goal should be to isolate the exponential expression. So in this case, the 2 to the t. I need to get that by itself before I can do log stuff. So how do I get that by itself? Divide both sides by 1,000. Okay, so 50,000 over 1,000 is 50. Over here they cancel, and I have 2 to the t. So 50 equals 2 to the t. To figure out what t is, variable trapped in the exponent, so I'm going to use Lincoln logs to get it down. Take the ln of both sides. Okay, so that means because I took the ln of 2 to the t, I can take the t down in front. Okay, I can only do that because I have taken the log of both sides, because I'm using a log to rescue that variable from the exponent. All right, so then ln of 2 is just a number. So to get t by itself, I can just divide by ln of 2. So over here we cancel, and you get t equals ln 50 over ln 2, which is approximately what? 5.6 years. So let's say you forgot to isolate the exponential expression before you took the log of both sides. Yeah, so let's see if it's possible. If I had 50,000 equals 1,000 times 2 to the t, and I just started by taking the ln of both sides. Yes, that's the log of a product, 1,000 times 2 to the t. And when you take the log of a times b, that becomes log of a plus log of b. Remember that from last class? So I could still do this. This would become ln of 1,000 plus the ln of 2 to the t. Right, and then I can move the ln of 1,000 over. So I'd have the ln of 50,000 minus the ln of 1,000 minus, yep, equals the ln of 2 to the t. Yeah, so then I can bring the t down on the right. I can bring this t down in front. Yeah, so now I can use another property of logs if I want. I could say, oh, yeah, you're doing the same thing, just using one property, and then you're undoing it after you do it. So another property of logs was that when you subtract two logs, you could condense it into a single log by using division. So this would be the ln of 50,000 divided by 1,000, which is 50, and we're back to the same equation we solved over here. So you can do it either way. It'll come out correctly as long as you remember your properties of logs. Right. All right, let's look at some of these ugly mixed equations here. So in part A, what do you notice about the two terms there? Yeah, there's an x in both of them, and what else do they have in common? E to the x. So I have an x in both and an e to the x in both, so I'm going to factor it out or reverse distribute it out, right? So if I have x e to the x, what should I put here so that when I distribute it, yeah, I'll get an x squared e to the x. It would be an x. And then over here, I just would have minus 5 equals 0. All right, so now I have three things being multiplied together, and the answer is 0. And when you multiply a bunch of stuff together and the answer is 0, it means one of them has to be 0. So we set each factor to 0 and solve it. So x equals 0, that's an easy one to solve. Over here we get x equals 5. And e to the x equals 0. When does e to the x equal 0? E is a constant, it's the number 2.7. So when x is 0, what is e to the 0? Anything to the 0 is 1.
It is what it is, because once you multiply it by 0.
Right, yeah. So if x is 0, we know the whole thing will be 0. Yeah. And if x is 5, we know the whole thing will be 0. Is there any other x that would make the whole thing 0? Will e to the x ever equal 0? Well, how do you solve an exponential? How do I find out what x? I could take the ln of both sides, right? So I have the ln of e to the x equals ln of 0. What's the ln of e to the x? X. What's the ln of 0? Let's see. What do you raise e to get 0? Well, that was the equation we were trying to answer in the very beginning, right? E to what gives you 0? So let's see, ln of 0, I get an error. Why do I get an error? There's nothing I can raise e to get 0 as an answer. If you raise it to 0, you get 1. Anything bigger than 0, and you're going to get bigger numbers. Smaller than 0, like even if I do negative numbers, is going to give me a fractional answer, right? So this never is 0. And we could also think about it in terms of the graph. So several classes ago, we looked at the graph of e to the x, and we saw that it looks like this, right? And the x-axis is an asymptote. It never crosses, so the y value of this function never equals 0. So e to the x will never be 0 because it never touches the x-axis. So my only solutions are x equals 0 and x equals 5. That make sense? All right. You try B. See if we can solve this one. All right, let's have a little look. So several approaches, right? I saw several people do different things. So make a little dividing line. I'm going to do 2 of the popular methods I saw. So one thing I saw people do is that they immediately saw that every term has a 10 to the x in it. Let's just divide it out. 10 to the x divided by 10 to the x. Divide both sides by 10 to the x. So normally I caution against dividing by a variable or an expression with a variable in it because you might inadvertently divide by 0, right? Because you don't know what the value of the variable is. But 10 to the x can never be 0, right? It's got an asymptote at the x-axis. It can never be 0. So I can do this division without any problems. And then I have cancel, 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 and I end up with x squared minus x equals 2, which is a quadratic equation. I can move the 2 over. And this factors x minus 2, x plus 1. And we get x equals -1 and 2. Other people moved the 2 times 10 to the x over first. I'll do it on another page here. So I have x squared times 10 to the x minus x times 10 to the x minus 2 times 10 to the x. Right, so this is another approach that I saw people doing. Move everything to one side first. Then each term has a 10 to the x in it, so you can factor it out. So you have 10 to the x times x squared minus x minus 2. I'm multiplying 2 things together, and the answer is 0. So either 10 to the x is 0, or x squared minus x minus 2 is 0. This is never. And this one we solved a couple minutes ago, -1 or 2. Okay, so that concludes solving exponential equations for the day. Now we're going to solve some equations that have logs in them. And the key is to isolate the logarithm, then change to an equivalent exponential equation. So I have 2 log of 5x equals 4. I want to isolate the logarithm expression first. So yes, but before you do that, to get the log of 5x by itself, I would have to divide by 2. So I have log of 5x all by itself equals 2. And then I want to change this to an equivalent exponential equation. So what would an equivalent exponential equation be? Close. So what's my base? So my base in my logarithm is 10. It's also the base in my exponential. So it's 10 to the something equals something else, right? Because my base in my log is my base in my exponential. And then my input and output in the log switch places for my exponential. So it was log base 10 of 5x equals 2. Now it's going to be 10 to the 2 equals 5x. When you don't have a base written, you assume it's a 10. Always. Yep. And when it's ln, you assume it's a log base e. So if 100 equals 5x, what does x equal? 20. Okay, let's look at B. I want to isolate my logarithm, right? But I have two of them. So let's at least collect them both on one side. So I'm going to have log base 2 of 4x plus log base 2 of x equals 2. And last class, we learned several properties of logarithms. One of them is when you add two logarithms that have the same base, you can condense it into a single logarithm where you multiply the two inputs. 4x times x is 4x squared. Okay, so now I've isolated a single logarithm. Log base 2 of 4x squared equals 2. Change it to an exponential equation. What's my base? 2. So 2 to the something equals something. Yep, the input and output switch, so my 2 comes over here, my 4x squared goes over here. So if 4 equals 4x squared, that means x squared equals 1, so x is what? 1 plus or minus 1, right? So let's double check the answers, right? I should have checked A too, I forgot. Let's check part A. Okay, so I want to make sure that 2 times the log of 5 times 20, because x is 20, that should give me what? 4. If I plug in my x equals 20 in here, I'm hoping to get 4 if I did it correctly. I do. Okay, good. So x equals 20 is really a solution. I'm going to, well, plug in each one separately. Yep. So for part B, oh, and it's log base 2. Shoot. I don't have log base 2 in my calculator. What do I do? Change of base. Yeah. So I'm going to have to do ln of 4x divided by ln of 2. Change of base to check it. So the ln of 4 times, let's do 1 for x, divided by the ln of 2. So that equals 2 when I plug in. And then I'm going to plug into the other side, and I should also get 2, right? So I'm going to do 2 minus the ln of 1 divided by the ln of 2. That's log base 2 of 1, just using change of base. And I also get 2. Okay, good. Let's try it when I plug in a negative 1. All right, so I'm going to do the ln of 4. Instead of 1, I'm going to put a negative 1. And I get a error. What's the problem? You can't take the log of a negative number. Yep. Think about the graph of the log function. It never crosses the y-axis. It looks like this. Look at the y-axis as a vertical asymptote. So I can't put in a negative x value. There's no y value. So we should reject the negative. X equals 1 is my only solution. I have an extraneous answer there. right, you guys try C. Okay, so for C, we have a similar approach to the last one. I'm adding two logs together. They have the same base. What is my base? 10, yeah. If there's no base written there, you assume it's a 10. So I'm adding two logs that have the same base. I can compress them into a single logarithm where I multiply the two inputs. So I'm going to have x squared minus 3x. And now I have a log equation. Single log equals a number. Change it to an exponential. So my base is 10. And then my input and output switch. So I'm going to have 10 to the first equals x squared minus 3x. 10 to the first is just 10. So this is x squared minus 3x minus 10 equals 0, a quadratic. You can factor it, and you get x equals 5 and negative 2. Yeah, you should test them both, right? When I put the 5 in, everything's cool, right? Log of 5, I can do that. Log of 5 minus 3, that's the log of 2, I can do that. But when I put the negative 2 in, I end up with taking the log of a negative in two instances. So I can't do that one. Just x equals 5 is my solution. All right, one more example of a log equation. In this case, I can't isolate, I can't make it look like log of something equals a number, right? So even when I compress the right side, I'm going to have the ln of x minus 3 equals the ln right? Oh, I guess I could. I could move one of the ln's over and it would be subtraction and I could do another division. I could, yeah. But, right. When you have the log of one thing equals the log of another thing, your two things have to be equal, right? So now I can just, it's kind of like canceling the logs. And then you just have an equation to solve with no more logs in it. Right, I could cross multiply and solve this. And I would get a quadratic. We won't go through the whole thing. So there's two basic approaches to solving the log equation. Make it look like log of something equals a number and change it to exponential. Or if you can make it look like log of something equals log of something else, you can set your two somethings equal to each other and just forget the logs. I just don't feel like it. All right. One more example where we do a little application. So the percentage of adult height attained by a girl who is x years old can be modeled by this equation. F of x equals 62 plus 35 times the log of x minus 4. And x is representing age from 5 years old to 15 years old. And f of x tells you what percentage of adult height is achieved. So let's do, what does that mean? That's a good question. So plug in an age, let's say 10 years old, right? So f of 10 would be 62 plus 35 times the log of 10 minus 4. So let's get a number for this. (62 plus 35 times the log of 6). Get about 89%. So that means that at 10 years old, a girl is approximately 89% of how tall she will eventually be. Yeah. So this is kind of how, this is an equation. If you ever went to the doctor as a kid and they said, oh, you're probably going to be like 5'6". You know, they can give you an estimate of how tall you will eventually be. this is the equation that they're using, right? So if this girl, if a 10-year-old girl shows up at the doctor's office and she's, I don't know, 4.5 feet tall, we would say, well, 89% of what is 4.5 feet? I would take 4.5, divide by 0.89. Oops. About 5.05 feet tall. Just about 5 feet tall. Say that again? Yes, that's true. That's why I said 4.5 feet, which would mean 4 feet 6 inches. Yeah, so this is 5.05 feet, right? So if I did 0.056 times 12, so it would be like 5.5 inches, something around there. 5 feet and a half inch, sorry. 5 feet, 6/10 of an inch. All right, so my question though is, at what age is a girl about 97% of her adult height? 14? How'd you figure it out? What did you do? So you replace f of x with a 97, and then we're solving for x, which is age. 35's cancel, right? Divide both sides by 35. Yep.
Which is 10 to the first.
Yeah. Add 4 to both sides. 14 years old. So 14 years old, you're about 97% of your full adult height. For girls, it's a different model for boys.